Hello, this is a continuation of essentially my solutions to exercise set 2 as well as discussion on unit hydrographs in general and how it applies to hydrology. As I said last time we left off, we're going to visit Chow, Maidment, and Mays, pages 201 to 242, and that has an entire section on unit hydrographs. Of course, I just forgot the page count. 201. And get to the correct section. So this is circa 88, so we're continuing forward from John Lienhardt's work and Sherman's work before him and Duge's work circa around the same time as Lienhardt, Bugs. And in this entire chapter 7, they present unit hydrograph, its definition, and the system model being simulated. Generally, we are dealing with a change in storage with time is equal to inflow minus outflow, and we're looking for various representations of that. So the easiest model is just a bucket model, similar to what you had in fluid mechanics, except the outflow term is no longer a Bernoulli's equation to get from inflow to outflow, and expand it by a various series expansion, make the necessary derivations, and we come up with a transfer function, which is generally what we're actually interested in, period. So our input time series is our rainfall, our output time series is our runoff, and our transfer function incorporates all the geomorphic properties that move us from inflow to outflow, all the loss properties, although in general loss is handled as a separate step, and what do I have left? I guess any hydraulic properties that affect the timing. And the timing is a large part of what's going on here. Then the chapter goes on to discuss responses of linear systems. Starts with an impulse response. So this part of the expression, u of t minus tau, is the kernel function or the unit hydrograph. It's called a kernel because that's the name of this function in this position in convolution. And then our excitation term is I. And then we integrate from 0 to real time. The value of I at some time shift multiplied by the kernel function at t minus the time shift with respect to the time shift, and that produces a output function at that particular time. And then this value of t is changing with time as we construct the integral. So there's a series of these definite integrals that are evaluated in order to produce that function. In hydrologic world, we are usually dealing with discrete instances rather than continuous, and the next part of the chapter demonstrates those discrete versus continuous, and we've done this in class already. Then it talks about a pulse response, and I will let you read the rest of it. What is of importance in this particular chapter is an attempt to illustrate the relationship between inputs and response on a pulse-by-pulse basis, which is the essence of convolution. It goes through a series of pages that discuss discrete convolution, and I will do that on my Dielmeyer here if it will allow me. There we go. So recall this picture, and so the idea of the unit hydrograph is, let's consider a single input. So we'll make this one time unit, otherwise unspecified, and we'll make this a depth unit. I don't know what letters, so we'll call it capital P. Then that unit has loss applied to it. Let's assume the loss is, again, we'll do 50% for the sake of clarity. Okay, this is 1 unit of excess. And typically the units used are inches or millimeters, and this is our unit of time. These are things like hours, or my preference is minutes. Now that one pulse at the outlet so the pulse has to have occurred before any outflow can begin. And for the sake of argument, let's assume that during this first time interval, not very much comes out. The second time interval, put the flow rate, the end of the second time interval, it's like that. First time interval, third time interval is like that. Fourth time interval, and then from then on it's 0. So the response of this unit of excess, here's our watershed, so we have that 1 unit distributed over the entire area, produces the response. The response, as I've drawn it here, looks something like that. And so 1 unit, 1 response. Now the reason the response looks the way it does, let me get all these area hash marks out of the way, and instead of just being a square wave like the input, is because some of the unit excess falls here, some falls here, some falls really close to the outlet. Stuff close to the outlet comes out pretty quickly. This other stuff takes time to get there, and this one back here takes even more time to get there. And so the response is reflecting the times. Now normally these are going to be in different scale units. So rainfall is usually in inches, and the time unit is either hours or minutes. So in terms of a rate, inches per hour. And then our discharge is typically in cubic feet per second or cubic meters per second. So the apparent scale of these is much different. But the area under this response curve is, it's cubic feet per second, the horizontal axis is time, then the area under that curve is a volume. If we take the excess input, multiply that by the total watershed area, that's also a volume. The two volumes need to match. That's simply mass balance requirement. Now this part of Chow, Mabit, and Mays explains how you would convolve multiple inputs. So in the case of our drawing picture, multiple inputs would be something like, here's our PT, and maybe there's an input here, There's another one here, another one here. I'll do a dumb looking storm. One like that, one like that. So time is moving this way. So that using our first peak, that produces our, can't remember what our hydrograph function quite looks like. This pulse produces this response. This next pulse produces a similarly shaped response, but it's time shifted and it doesn't get quite as high. This third one produces yet another one that's time shifted and even not quite as high still. Fourth one produces one that's kind of similar to that second one. And the fifth one produces a little dinky one. Then the convolution process is pulse, response, pulse, response, pulse, response. Lay all those out on the time axis, and then for each time we add up all the non-zero components of response to get the envelope, which is the observed hydrograph. So this point goes something like that, and then that next part comes on. So as we're going up here, we get a little additional one here, so it gets up to that higher part, and our resulting net hydrograph might look something like that. Doing this as a quickly sketched out notes, it's reasonably hard to convey the process going on, but it's fairly straightforward reading the book. And this pulse produces a triangle, this pulse produces a different triangle. We add the two triangles together along the space thing, and the combined total triangle image is the response hydrograph. So this describes how that convolution is done in discrete space. It has the main features of the transfer function. Excess rainfall is constant intensity over the effective duration. Effective duration is one of those time pulses. The rainfall is uniformly distributed over the entire area. That assumption goes to crap as the areas get really big. But stuff on the 10 to 20 square mile range is plausible. The base time of the direct runoff hydrograph is constant. So it means that those triangle bases don't change for a given watershed in a given effective duration. The ordinates of a common base time are proportional to the total amount of each hydrograph, which means that those triangles, the tallness of the triangle is directly proportional to the rainfall intensity value. And for a particular watershed, the hydrograph resulting reflects time invariant characteristics of a watershed. So we're assuming that the watershed doesn't change. Certainly in human time frames, that's probably a reasonably good assumption. And the author goes on to explain a little bit more of what's going on. And our linear system comparison is shown here, and this graphic is demonstrating that what we consider a linear system in signal processing has direct analogs in the watershed signal processing, where it's processing the signal from excess precip to direct runoff. Then it describes how to deconvolve real data, which is something we're going to do later on in your exercise set. It has the discrete time convolution equations. There's an example. It's in your best interest to work through this example by hand. By hand, I mean do it on a computer spreadsheet. And once you've done that, you will have half the tool available to you that you need. Now, in this particular instance, the time step is 1/2 an hour, 30 minutes. The precip is given here as excess precipitation. The unit hydrograph ordinates are already converting to cubic feet per second per inch. That's one way of doing it. A just as correct, and in my mindset, more logical way is we convert the direct runoff into watershed inches per unit time. So we would take the direct runoff, 808 cubic feet per second, divide by the square feet of the watershed, which we get from the watershed area. That would give us watershed feet per second, and then multiply that number by 12. That gives us watershed inches per second. That way, the inputs and the outputs are in the same units. If you choose not to do that, you have to keep track of cubic feet per second, and getting your volumetric checksums is a little more of a challenge. I mean, it's just a multiplication of a particular constant related to area. And you can go through this procedure yourselves as you're reading this document. And then the author shows how to obtain estimates of the unit weights from observations of precipitation and runoff. That's analysis. Matrix calculation is one way. Linear regression is another. Linear programming is a third. Trial and error is legitimate, but can be slow if you make a really bad first guesses. And you could conceivably go from a regression part by not necessarily doing linear, but doing a nonlinear regression and using a package that will alternately adjust parameters of your hydrograph to make your observed and your model as close together as possible. So you want to read this chapter pretty carefully. Now where we're headed to, the synthetic unit hydrograph, very much the same ideas, but what it is aimed at doing is asking the question and providing the answer, can we take other metrics of the watershed, area, main channel length, main channel slope, mean annual precipitation, etc. A lot of those things that were used for the regression equation, and use those to determine the various values in our unit hydrograph function independently of actual observations. And that has great utility for both engineering and environmental engineering application of hydrologic processes, because rainfall is relatively easy to come by. Runoff measurements, when you get away from a formal gauging station, are not easy to come by. But we still have to estimate flows at places that we can't gauge them. So you all will read that as part of your exercise. Then we get into some self-serving stuff. Hopefully it's going to... first one is instantaneous unit hydrographs. You'll notice that expression right there is unreadable because it's too small. There we go, Zoomster. Nope, where's my Zoommeister? Apparently zooming is not an option. Like all things on the mighty computer, you touch something and it breaks it. I'm going to choose the alternate link. Yeah, that gives me a localized copy. So this equation should look very familiar. Again, the kernel and the excitation. Some discussion on data assembly. And then the unit hydrograph that was used for this paper, the kernel function, is this rascal. we'll approximate that by, we'll leverage that. The key thing here is we have time over some characteristic time, and we have a decaying exponential raised to some power. In this case, the power is 2, and this capital N is what I call the reservoir number from Nash's development, and these don't necessarily have to be integer, although n probably should be, and these exponents are not constrained to be 2, although that's fairly common. And then this goes and looks at a few special cases. One of the important special cases is the NRCS dimensionless unit hydrograph, which is in common software, and the function just presented with a reservoir number somewhere between 1 and 3, 2, are very similar. So you could conceivably use this with the reservoir number capital N here set to, looks like 2.5, would be a good approximation of the NRCS hydrograph. I think that's explicitly stated in the paper, or maybe it should have been. Looks like it was not explicitly stated in the paper. Perhaps an oversight on the authors, or possibly the reviewers required the authors to take it out. In this expression here, A is the area of the watershed, so that converts this right-hand side, which is going to produce results of inches per unit time, multiplied by the watershed area, and that gets us discharge in conventional discharge units. There's some other unit conversions buried away in these constants, but that's all that's going on. If you take the area out front, what's in the integral is essentially a probability distribution, so it has to integrate to 1, and then we adjust that by the watershed area to get the correct flow units. And here's some examples. So the key thing out of this paper from the standpoint of the exercise set 2 is that function, or let's see if there's a better representation of it, or this function, the actual internal response hydrograph. Excuse me, not the kernel function that's going to be used in the convolution. And we'll see how that appears shortly. The next two readings are more looking forward. This is an attempt to synthesize the unit hydrographs from a digital elevation model. So make that step from data analysis to being able to predict what the hydrograph parameters should be. And then the last part, Broussard, chapter 12, ties everything together. So that would be the first part of exercise set 2 that you'll be working on.